Hello and welcome to the section 3.7 video lecture. Today we're going to talk about implicit differentiation. So far we've been talking about doing derivatives where what we were dealing with was a function. And what we want to look at is, well, what if we don't have one variable is equal to an expression of the other? What if we have two expressions that are equal that involve both variables or more than two variables? And that's where implicit differentiation comes in. So, just like always, you can take out your note sheets, which can be found on my math lab under handouts or in Blackboard under this week's information, and you can follow along with those, or you can just use regular notebook paper. So to start this out, so let's talk about how implicit differentiation works. Basically, we differentiate both sides of the equation with respect to x, treating y as a differentiable function of x using the chain rule. So basically what we say is something similar to this. Basically, the implicit differentiation, the chain rule we were doing here. We're dealing with functions that look like this, but we're going to differentiate them with respect to x. So when we do that, we're going to be left with some function that we have to deal with the derivative of. But in this case, we have an expression for it that involves x. That is not going to be the case with implicit differentiation. So after you do that, what you're going to do is solve for dy over dx, basically. Collect the dy dx on one side of the equation and solve for it. So to show you an example of this, let's deal with an equation that we could do either way. So if y squared equals x, first find dy dx by solving the function for y and find the derivative of both sides. Okay, so let's try that. So we've got this equation. It's not a function, but I could write it as two functions actually by writing it as y equals plus or minus the square root of x. Right, so we get both of those. So then we take, so we end up basically having two different functions we have to take the derivative of. Y equals the square root of x and y equals the negative square root of x. And luckily for us, these are functions we've taken the derivative of quite a few times already. We know that the derivative of the square root of x is 1 over 2 root x. So the derivative of negative root x would be negative 1 over 2 root x. Okay, so that's one way we could solve this. But we could also use this idea of implicit differentiation. So in this case, what we do is we take the derivative of both sides with respect to x. So remember, this is what that means. We're taking the derivative and we're taking it with respect to this variable on the bottom. Okay? The derivative on the right-hand side is very straightforward, right? The derivative of x with respect to x is just 1. Over here is where, on the left-hand side, is where this implicit differentiation idea is going to come into play. So what we want to do is we want to take this derivative exactly the same way we would take it using the chain rule. And the way we would do that, right, is we'd say, okay, what's the derivative of something squared? Well, the derivative of something squared is we use the power rule, and then that's 2y, right? And I ignore what's on the inside, and then I take the derivative of what's on the inside. Right, that's the chain rule. That's what we were looking at in the last section. Now, if I look at this, what is the derivative of y with respect to x? Well, I don't have a good way to find a numerical value for that because it doesn't have x's. This y doesn't have an x, so I can't use my differentiation rules, but I do have a symbology that I can use to write the derivative of y with respect to x, and it's simply dy over dx, right? And now we can solve for dy over dx by dividing both sides by 2y. So dy over dx equals 1 over 2y. And so there is our derivative using implicit differentiation. Now, what you should notice is these are exactly the same. Right? This and this are the same. Because if we know y is plus or minus the square root of x, so if I substitute that in there, right, we get the exact same thing. Okay, so that's one example of this working. Now, we're mostly going to use differentiation of this implicit style when we can't do what's happening on the left-hand side here easily, when we can't solve for y. Very easily. So, let's look at some examples. Okay, so here's an example of an equation that we could solve. We could try and solve for y, but it would be pretty difficult. So what we want to do instead is we want to use this implicit differentiation. So we take the derivative of both sides with respect to x, Okay, so we use the first thing we do here is we use the sum and different rules. So this is d dx of x cubed minus d dx of xy plus d over dx of y cubed equals the derivative of 1, which is just 0, right? The derivative constant is 0. So now we can do these three derivatives. The derivative of x cubed with respect to x, those are the same variables, so that means I just use my differentiation rule. So the derivative of x cubed with respect to x is 3x squared. In the second one, I have a product, so I need to use the product rule. So the product rule tells me that I'm going to take the first thing times the derivative of the second thing plus the derivative of the first thing times the second thing. And then we need to do the derivative of y cubed with respect to x. Well, these variables don't match up. The x here and the y here. So that means I'm going to have to use the chain rule. So the derivative of y something cubed is 3y squared. And then I still have the derivative of y with respect to x. Okay, so that's using the chain rule. Because these variables don't match up, I have to use the chain rule to find the derivative of the function, and then I'm going to deal with this y. So then we get 3x squared minus, well, what's the derivative of y with respect to x? Well, it's dy dx. The derivative of x with respect to x is 1, so this would be, and we have to distribute the negative, so minus y plus 3y squared. And then what's the derivative of y with respect to x? Well, it's dy over dx equals 0. Okay, so now we're going to come up here where I've got some more room. And so now what we want to do is we want to start solving for dy dx. So we want to subtract 3x squared from both sides and add y to both sides. Right? So we want to isolate these, the terms with dy dx's. Okay, and that's what we're going to write up here. So these cancel. And I'm going to rewrite this with positive terms. So it'd be 3y squared dy dx minus x dy dx equals y minus 3x squared. Okay, so now that we've isolated all the dy dx's, we want to get those out of these terms, and we can do that by factoring. So this would be dy dx times 3y squared minus x equals y minus 3x squared, and then we can divide by 3y squared minus x. So we get dy dx equals y minus 3x squared over 3y squared minus x. Just like that. Okay, and so that's going to be the idea here of how we're going to do this implicit differentiation. Okay, so let's try another one. So the second one, same idea, right? Take the derivative with respect to x on both sides. So on the left-hand side, those variables match up, so I just do normal differentiation. So 3x, the derivative of x cubed is 3x squared. On the left-hand side, I'm going to need to use the quotient rule. So it's the bottom times the derivative of the top minus the derivative of the bottom times the top all over the bottom squared. Okay, so let's go ahead and work that out. So x plus 3y times the derivative of this. So the derivative of 2x is 2. The derivative of y with respect to x is dy dx. Okay, minus the derivative. So the derivative of x is 1. The derivative of 3y with respect to x is 3 dy dx times 2x minus y all over x plus 3y squared. Okay, so now we need to keep going. We need to get these dy dx's out of the denominator, out of these parentheses. So there's a couple things I want to do, I think, here. I want to start isolating the dy dx's. So one thing I can do is multiply both sides by this denominator to move it to the left-hand side. And the other thing I want to do is I want to distribute. So we've got 3x squared times x plus 3y squared equals, and then distribute these out. So 2x minus 2 dy dx plus 6y minus 3y dy dx. And then the other side. And all of these ones are going to be the opposite of what I would normally get because of this negative. So 1 times 2x is 2x, but it's the opposite of that. So minus 2x. 1 times negative y is negative y. The opposite of that is positive y. 3 dy dx times 2x is 6x dy dx, but it's going to be negative. So negative 6x dy dx. And then 3 dy dx times y is negative 3y dx, but it's going to be the opposite of that. So plus 3y dy dx. Okay, now we're not going to do anything on the left-hand side, but on the right-hand side, I'm going to combine like terms. So I've got a 2x, negative 2x. So those cancel. I've got negative 3y dy dx and a positive 3y dx. So those cancel. And then everything else I can combine a couple things together. So 6y plus y is 7y. Minus 2 dy dx minus 6x dy dx. Okay. Let's see. Where's the best place to do this? Probably up here. We'll try and write it up here in the upper left. So we're going to take this and come up here somewhere. So now you're going to move the 7y over to the other side, right? So you can get the dy dx's by itself. So it'll be 3x squared times x plus 3y squared minus 7y equals negative. Well, and we could actually factor out the dy dx here if we wanted to. So dy over dx times negative 2 minus 6x. And then just divide both sides by negative 2 minus 6x. So this will be 3x squared times x plus 3y squared minus 7y over negative 2 minus 6x equals dy dx. And there's the answer. Okay, so that one was pretty complicated because we had division going on and we were using the quotient rule and all kinds of stuff like that. But that's the general idea. Okay, so let's try one more together before I have you guys try a few, and then we'll talk about finding second derivatives. Okay. So the last one here, we want to take the derivative of both sides, and so we're going to have to use the product rule. So I'm going to skip writing out this first step, and I'm just going to go right into doing the product rule. So for the first side, I've got the first thing times the derivative of the second thing. So that's the derivative of cosine of 2x plus 3y plus the derivative of the first thing times the second thing equals, and then I have to do the product rule on the other side. So y times the derivative of sine x plus the derivative of y times sine x. Okay. So the derivative of cosine x, I have to use the quotient, the chain rule. So the derivative of cosine is negative sine, so negative sine 2x plus 3y times the derivative of 2x plus 3y plus the derivative of x is just x, so that's just 1, sorry, so that's going to be cosine of 2x plus 3y. On the left-hand side, the derivative of sine is cosine, so this will be y cosine of x, and the derivative of y with respect to x is dy dx sine x. Okay, and now we can do this derivative, the one derivative we still have left. So this will be the opposite of x sine 2x plus 3y times the derivative of 2x is 2. The derivative of 3y is, with respect to x, is 3 derivative of y with respect to x plus the cosine of 2x plus 3y equals y cosine of x dy plus dy dx sine x. Okay. Now, what you should notice in here is we've got we need to do some distribution. So if we distribute this inside this parentheses, we get negative 2x sine 2x plus 3y minus 3x sine 2x plus 3y dy dx plus cosine, and everything else stays the same. Okay, as the previous step. So now we want to collect, except I put a plus somewhere where I should put an equals right here. Equals y cosine x. So now we want to collect the dy dx's on one side and everything else on the other, and I'm going to reorder some stuff so that my positive terms come first. So I'm going to subtract y cosine of x from both sides. So the left, and I'm going to add 3x sine 2x plus 3y dy dx. So I'm moving this to the right and I'm moving this to the left. So this will be cosine of 2x plus 3y minus 2x sine 2x plus 3y minus y cosine x equals, and I could go ahead and factor out the dy dx because both these terms have a dy dx. I'm just trying to save on some space because I'm almost out of space. So dy dx times sine x plus 3x sine 2x plus 3y, and then divide both sides by this. So we end up with cosine of 2x plus 3y minus 2x sine of 2x plus 3y minus y cosine of x all over sine of x plus 3x sine of 2x plus 3y equals dy dx. And these second two we just did together are about as bad as these are going to get. Okay, so if you can do those, if you followed along with that, you should be good to go. And if you can do the ones on the next page, then you're probably fine. You're probably good to go with this as well. So go ahead, flip over to this page, pause the video for a moment, and try these 3 problems. And then once you're done, hit play, and we'll go through them together. So, same idea as what we did before, right? So start out by taking ddx of both sides. Okay, so on the left-hand side, we're just using the sum and difference rule. So ddx of x cubed plus ddx of y cubed. And on the left-hand side, I have to do the product rule. So this will be the first thing, 18x times the derivative of the second thing, so the derivative of y, plus the derivative of the first thing times the second thing. Okay, so let's do all those derivatives. So the derivative of x cubed with respect to x is 3x squared. The derivative of y cubed is the same idea, except that I'm doing it with y instead of with x. So I get 3y squared, but I'm doing the derivative of y, so I have to do the chain rule. So this will be 3y squared times the derivative of y with respect to x. Times 8 equals 18x times the derivative of y with respect to x plus the derivative of 18x is 18, so 18y. Okay, and now we're going to solve for dy dx. So subtract 18y from both sides and subtract 3y squared from both sides, dy dx. Factor out the dy dx. And then divide both sides by 18x minus 3y squared. So dy dx equals 3x squared minus 18y over 18x minus 3y squared. Okay, so there's the first one. Second one. Take the derivative of both sides. Left side, use the chain rule. So it's 2 times 3xy plus 7 times the derivative of 3xy plus 7 equals, the derivative of 6y is 6 dy dx. Okay, then you could go ahead and distribute the 2 here, so it's 6xy plus 14. And then here I have to do this derivative. So that's going to be the derivative of 3xy, because the derivative of 7 is 0. And now we have to use the quotient rule. I mean the product rule, sorry, because that's a product. So it'll be 3x times the derivative of y with respect to x plus the derivative of 3x times y. Okay, so we can do that. So this is 6xy plus 14 times 3x dy dx plus the derivative of 3x with respect to x is 3. So 3y equals 6 dy dx. And now we need to distribute on the left-hand side, so we can get rid of all those parentheses. So this would be 18x squared y dy dx plus 18xy squared plus 42x dy dx plus 42y equals 6 dy over dx. And now we need to collect the dy dx terms on one side and everything else on the other. So I'm going to subtract the dy dx terms over to the right-hand side. So this would be 18x y squared plus 42y equals 6 dy dx minus 18x squared y dy dx plus, minus 42x dy dx, and then factor out the dy dx. So 18xy squared plus 42y equals dy dx times 6 minus 18x squared y minus 42x, and then we can divide both sides by this. So dy dx equals 18xy squared plus 42y over 6 minus 18x squared y minus 42x. Okay, so that's that one, and then the last one. So the last one, same idea. Take the derivative of both sides with respect to x. Sorry. Okay, so on the left-hand side, use the product rule. So x times the derivative of y with respect to x plus the derivative of x with respect to x times y. And on the left-hand side, we have to use the chain rule. So the derivative of the cotangent is negative cosecant squared xy times the derivative of xy, which is nice in a way because it's the same as what's on the left-hand side, right? What I did up here. So this derivative right here is going to be the same as whatever I get over here. So on this side, this is x dy dx plus the derivative of x with respect to x is 1, so plus y. And so on the left-hand side, I get the same thing multiplied by this negative cosecant squared. So x dy dx plus y. Okay. So then we're going to distribute. Okay, so we can distribute on the left-hand side. So x dy dx plus y equals negative cosecant squared xy times x dy dx and minus cosecant squared xy plus y. Okay, and so now we want to get the dy dx's on the same side, so move this to the left and y to the right. So x dy dx plus cosecant, let's call it x cosecant squared xy dy dx equals Well, if I'm subtracting, sorry, I added a plus in there that shouldn't be there. This should just be times y. And then I'm subtracting y over here, so I got negative y minus cosecant squared xy, and I'm going to move the y out in front like I did with the x because that makes more sense to me where it should be. And then we can factor out the dy dx. So this ends up being x plus x cosecant squared xy equals negative y minus y cosecant squared xy. And then we can divide. So dy dx equals negative y minus y cosecant squared xy over x plus x cosecant squared xy. And if you look at those and you say, wow, those kind of look similar to each other, they should, because if I factor out a negative y on top and a positive x on the bottom, what you should notice is now I have two factors that are the same. So these cancel, and it turns out the derivative of this is just the opposite of y over x. So it seems like a pretty complicated thing to start out with, but its derivative is a fairly simplistic expression in the end. Okay, so that's it for first derivatives. Okay, so now let's talk about second derivatives and how you find those. So if I want to take this more than one step, this works kind of similar to what we've done before. You just take the derivative again. So let's go and look at that. But there is a little bit of a kink to doing these. So let's go and look at these. So they start out exactly the same way. The first part of this is exactly the same as what we just did. Take the derivative with respect to x on both sides. Okay. So the derivative of y squared with respect to x is 2y dy dx. Derivative of negative 2x with respect to x is just negative 2. The derivative of 1 with respect to x is 1. The derivative of negative 2y with respect to x is negative 2 dy dx. Okay? Then we're going to do the same thing we've done previously. I'm going to get the dy dx on the left and put everything else on the right. So that means I'm going to add this to both sides, and I'm going to subtract this. So this will be 2y dy dx plus 2 dy dx equals 2. Factor out the dy dx and divide both sides by this. So dy dx equals 2 over 2y plus 2, and then you can cancel out a 2. So dy dx equals 1 over y plus 1. Okay, so that's the first derivative. So then to find the second derivative, you do what you might expect, which is do the derivative again. So d dx of dy dx equals the derivative of 1 over y plus 1. On the left-hand side, the derivative of y with respect to x is just the second derivative of y with respect to x, which is, that's the notation, right? The d gets squared, and on the bottom the x gets squared. And then on the right-hand side, I have to use the quotient rule. Or, if you prefer, you could also use the chain rule, which might actually be easier here. But the more obvious way to do this is with the quotient rule. So that's going to be y plus 1 times the derivative of 1 minus the derivative of y plus 1 times 1 over y plus 1 squared. Okay. So if we do that, the derivative of 1 is 0, and 0 times anything is 0, so that part's just going to go away. The derivative of y plus 1 with respect to 1 is just negative dy dx, right? The derivative of y with respect to x is dy dx, and it's the opposite of that because of this negative right here. And then the derivative of 1 is 0, and if we multiply that by 1, we get this, over y plus 1 squared. Now, the question is, do we really want dy dx in our answer? And the answer to that is no. So what we can do, though, is we should notice that we know what dy dx is already. So we can substitute that in here and simplify. So the second derivative of y with respect to x would be negative 1 over y plus 1 over y plus 1 squared. And then if you combine these, you multiply by the reciprocal. So this would end up being the opposite of 1 over y plus 1 cubed. Okay, so we're going to skip the one at the bottom of the page here because I keep not taking out the notes, but I probably should because it's really more complicated than it's necessary. This one, even though it doesn't look it, ends up being very big and hard and unnecessary. So let's go ahead and flip to the next page and let's look at the, let's go ahead and do one more of these together and then I'll have you guys try the other one that I believe are a little more easier and straightforward and more what we're going for. So let's try another. So start off once again by taking the derivative with respect to x, right? Just like we normally would. And then the only thing you have to be careful about is anytime you're doing a derivative that doesn't match this variable. So derivative of x to the 2/3 should be 2/3 times x to the negative 1/3, right? We bring the exponent out front and then subtract 1 from the exponent, plus 2/3 times y to the negative 1/3 dy dx, right? Because I took the derivative of y with respect to x, so I get a dy dx equals 0. Okay, and then we want to solve for dy dx. So subtract this term from both sides. So we get 2/3 y to the negative 1/3 dy dx equals negative 2/3 x to the negative 1/3, and then divide both sides by this. So we get dy dx equals negative 2/3 x to the negative 1/3 divided by 2/3 y to the negative 1/3, and then the 2/3 cancel. So dy dx is negative x to the negative 1/3 y to the negative 1/3. Okay, so now that we've done that, go ahead and find the second derivative, right? So we'll come up here and we'll take the derivative of both sides again. So that's the second derivative of y with respect to x. And on the left-hand side, we have to use the quotient rule. So the negative just goes out in front of the whole thing, and then it's the bottom times the derivative of the top minus the derivative of the bottom times the top, all over the bottom squared. Okay, so then we do those derivatives. So the negative's still all the way out in front. So y to the negative 1/3. The derivative of x to the negative 1/3, you multiply, remember, by the negative. The exponent comes out in front, so then and then you subtract 1. So that's negative 1/3 x to the negative 4/3 minus the derivative of y to the negative 1/3. Works exactly the same way, except you get a dy dx and then times x to the negative 1/3 all over y to the negative 2/3. Okay, so then we need to do a couple things. We need a substitute in here for using this expression, and then we can do some simplification. So d squared y over dx squared equals the opposite of negative 1/3 y to the negative 1/3 x to the negative 4/3 plus 1/3 y to the negative 4/3 times negative x to the negative 1/3 over y to the negative 1/3 times x to the negative 1/3 all over y to the negative 2/3. Okay. Okay, and then there's just one thing I want to fix here because that got too close together. So that's a negative, right? Because this had a negative in it. Okay, so now what we can do is we can do some simplification. So d squared y over dx squared equals negative 1/3 y to the negative 1/3 x to the negative 4/3 plus, it's going to end up being minus because of this negative in here. So minus, and now we need to multiply these all together. So y to the negative 4/3 divided by y to the negative 1/3. Remember, you subtract exponents. So that's going to end up being y to the negative 3/3, which is y to the negative first. So this will be 1/3 y to the negative first. And then x to the negative 1/3 times x to the negative 1/3 is x to the negative 2/3. All over y to the negative 2/3. And so now we can do a few things to finish this problem off. First off, I can divide these y's in each one of these terms, okay, so that I can simplify this a little. So y to the negative 1/3 divided by y to the negative 2/3, you subtract the exponents, so negative 1/3 minus negative 2/3 is y to the 1/3. Okay, and then over here, y to the negative first time divided by y to the negative 2/3 is you subtract, and so that's going to be y to the negative 1/3. And then the other thing that happens here is we can distribute this negative. So negative times negative is a positive 1/3. Negative times a negative is a positive 1/3. Okay, so this ends up being, this is our answer for the second derivative. So that's not really straightforward, but it's more straightforward than the one on the previous page at the bottom that we skipped would have been. So go ahead and pause your video for a second and try doing this bottom one on your own, and then when you hit play, we'll go through it together. Okay, so here we go. So take the derivative of both sides with respect to x. Okay, so we have to do the product rule, right? So x times the derivative of y plus the derivative of x times y plus the derivative of y squared equals 0. So the derivative of y with respect to x is just dy dx, plus the derivative of x with respect to x is 1, so plus y, plus the derivative of y squared with respect to x is 2y dy dx equals 0. And then move the y to the other side to get the dy dx's all together and factor out dy dx. So this is dy dx equals times x plus 2y equals the opposite of y, and then divide by x plus 2y. So dy dx equals the opposite of y over x plus 2y. Okay, then we do the second derivative. So d dx of dy dx equals d dx of negative y over x plus 2y. So that's d squared y over dx squared equals, and we use the quotient rule. So x plus 2y times the derivative of negative y minus the derivative of x plus 2y times negative y all over x plus 2y squared. Okay, so the derivative of negative y with respect to x is negative dy dx. And the derivative over here is we get 1 plus 2 dy dx times negative y. And then we're going to multiply that. So x plus 2y squared. So d squared y over dx squared equals the, and you can distribute this. So negative x minus 2y dy dx. And then over here, we get plus y, when I distribute the negative and the negative, plus 2y dy dx over x plus 2y squared. Oh, and I forgot the dy dx here, which is going to be important. And so the negative 2y dy dx and the positive 2y dy dx cancel. So this is d squared y over dx squared equals the opposite of x, dy dx plus y over x plus 2y squared. And now we simply have to substitute in dy dx. And I'm running out of room here, so I'm going to come over here and I'm going to simplify across. So d squared y dx squared equals the opposite of x times the opposite of y over x plus 2y plus y all over x plus 2y squared. And now I need to get rid of this complex fraction, so we're going to multiply by the least common denominator. So that's multiplied by x plus 2y over x plus 2y. So for the first term, the x plus 2y canceled, so it's x times y, which negative x times negative y, which is xy. And then here I have to distribute. So I get y times x is xy, and y times 2y is 2y squared over x plus 2y cubed. And so this will be 2xy plus 2y squared over x plus 2y cubed. Okay, and so that's it. That's the answer. Okay, so that's a little challenging, but that's how you do those. So with practice, you'll get the hang of that too. Okay, so then the last thing in this section is just bringing this all back to this idea of what it has to do with tangent lines, because these still have, even though these are weird, they still have tangent lines. So that's what we're going to talk about on page 41. So as with all other derivatives, what they tell us is that they tell us what is the slope of a line tangent to the curve at that point. That's one of the definitions of the derivative. So even with things that aren't functions where we're using implicit differentiation, we can still do this. And so that's what we want to look at here. So it says, verify that the given point is on the curve, and then find the lines that are tangent and normal to the curve at that given point. So, first thing I want to just say is a reminder. I think you've seen this in the homework before. Normal just means perpendicular to the line at that given point. So let's check and make sure this works. So it's 0 plus 2. Nope, that's definitely not the right point. So let's see. Well, let's just change. I think this will work as the point if I just change that to a 2. So there's just a typo in this problem. So let's do that, and let me make sure that works. So 0, 0, that becomes plus 2, so minus 2. Yeah, so that's fine. So that works. So now we're good. So what you have to do to find that out is you first have to find the slope of the line that are tangent. So that means find the derivative. So take the derivative of both sides. Okay. So this will be the derivative of y squared is 2y dy dx. Derivative of negative 2x is negative 2. Derivative of negative 4y is negative 4 dy dx. And the derivative of negative 2 is 0. Derivative of 0 is 0. Okay. Then add 2 to both sides and factor out dy dx. So dy dx equals 2y minus 4. I mean, not equals, sorry. Times 2y minus 4 equals 2, and then divide by 2y minus 4. So dy dx equals 2 over 2y minus 4. Okay, so that's the equation for the slope of a tangent line at any given point. So to find the slope of the point we want, negative 1 comma 0, we just plug in our y value. So our slope is just going to be 2 over 2 times 0 minus 4. So that's 2 over negative 4, or negative 1/2. So that means we want to write a line that has a slope of negative 1/2 and goes to the point negative 1 comma 0. So we just plug that into point slope form. So y minus 0 equals negative 1/2 times x plus 1. and distribute, and you get y equals negative 1/2 x minus 1/2. Okay, so that gives us the line tangent to it. And then if I want to find the line perpendicular, I just need to find the opposite reciprocal of this slope. So that means the slope of our normal line is going to be positive 2, right? We flip it over and do the opposite. And it's still going to go through this point. So that would be y minus 0 equals 2 times x plus 1. So that's y equals 2x plus 2. And that's really all there is to that. So this is just using the definition of the derivative as the slope of the tangent line at a given point. Okay, so let's try another one. Same idea. So start out, check and make sure this works when you plug it in. So if I plug this in, I get 0 minus 0, so that equals 0, so we're all good. So find the derivative of x squared cosine squared y minus sine y equals the derivative of 0. So I have to use the product rule to start out. So x squared times the derivative of cosine squared y minus, the derivative of x squared times cosine squared y minus the derivative of sine y equals 0. So the derivative of cosine squared y, we're going to have to use the chain rule a couple times here. So first, we take the derivative of the outside, which is this squared. So that'll be 2 cosine y. Then we take the derivative of the cosine, which is negative sine y. And then we take the derivative of y, which is dy dx. Over here, we take the derivative of x squared, which is 2x cosine squared y. And then we take the derivative of sine y, which is cosine y. Okay. And so now we're going to solve for dy dx. So what you want to do is you want to move these to the other side, and then we're going to divide. So this will be negative 2x squared cosine y sine y dy dx equals cosine y minus 2x cosine squared, cosine squared y, and then divide. So dy dx equals cosine y minus 2x cosine squared y over negative 2x squared cosine I have a concern. Oh, I left out a dy dx. That's why. Okay, good. Sorry, I have to go back a step because I screwed it up. So let's fix this. Sorry about that. So this should be the derivative of sine y is cosine y dy dx. I forgot the dy dx because I just did the derivative of sine x versus the derivative of sine y. So now we're just going to move this piece to the other side. And now we can factor out the dy dx and divide. So this will end up being dy dx equals negative 2x cosine squared y over negative 2x squared cosine y sine y minus cosine y. Okay. And now we just plug in 0 and pi, and that'll give us our slope. So this will be negative 2 times 0 times the cosine squared of pi over negative 2 times 0 squared cosine of pi sine of pi minus cosine of pi. And in the end here on the bottom, we're going to get negative 1. And on top, we're going to get positive 1. And on the top, we're going to get 0. So the slope will end up being 0. And so what we end up with is a horizontal and a vertical line. So horizontal line that goes through the point 0 comma pi is just going to be y equals the y coordinate. So y comma pi. And a vertical line that goes through the point 0 comma pi is just going to be x comma 0. So here is my tangent, and here is my normal line. Okay, So that's the idea. So go ahead, go ahead and try the 2 problems on page 42, and then that'll be it for this section. Okay, so now you've had a chance to try them. Let's go through these together. So you can check and make sure that point works. It does. So we're just going to take the derivative of both sides with respect to x. So derivative on the left-hand side is 2x plus 2y dy dx equals 0. Subtract 2x from both sides, so 2y equals dy dx equals negative 2x. Divide by 2y, and you get dy dx equals negative x over y. So our slope is just going to be negative 3 over negative 4, which is 3/4. So we do m equals 3/4 with the ordered pair 3 comma negative 4. So that's y plus 4 equals 3/4 times x minus 3. So y plus 4 equals 3/4 x minus 9/4, and then subtract 4 from both sides. So y equals 3/4 x minus 25/4. Okay, and then the other one, to do the normal line, we take the opposite reciprocal of 3/4, which is negative 4/3, and we use the point 3 comma negative 4 still. So this will be y plus 4 equals negative 4/3 times x minus 3. So that's y plus 4 equals negative 4/3 x plus 4. Subtract 4 from both sides, and you get negative 4/3 x equals 0. I mean, not equals 0. Negative 4/3 x. Because the 4's cancel out when you subtract 4 from both sides. Okay, so there we go. Okay, and then the second one should be basically the same idea, except a little trickier. So this will be the derivative of x squared minus the square root of the square root of 3xy plus 2y squared equals the derivative of 5. So this is 2x. We have to do the product rule in the middle. So minus root 3x times the derivative of y plus the derivative of the square root of 3x times y plus the derivative of 2y squared, which is 4y dy dx, equals the derivative of 5, which is 0. Okay, so we get 2x minus root 3x dy dx plus root 3y plus 4y dy dx equals 0. Move these two terms to the right side, and so we get dy dx times 4y minus root 3 equals negative 2x minus root 3y, and then divide by 4y minus root 3. So dy dx equals negative 2x minus root 3y over 4y minus root 3. X, sorry. Yeah, I knew I forgot something. There's an X. Yeah, the X, I left that out. The X that's right there. So now we just plug in these ordered pairs. So our slope is going to be negative 2 times root 3 minus root 3 times 2 over 4 times 2 minus root 3 times root 3. So I'm getting an m of negative 4 root 3 over 8 minus 3, which is 5. So negative 4 root 3 over 5. Yeah, that seems fine. Okay, so then we're going to do a slope of negative 4 root 3 over 5 with the point root 3 comma 2. So that's going to be y minus 2 equals negative 4 root 3 over 5 times x minus root 3. So that's y minus 2 equals negative 4 root 3 over 5x plus root 3 times root 3 is 3 times 4 is 12, so 12 fifths. And then add 2 to both sides. So negative 4 root 3 over 5x plus 16, plus 2, so plus 10 fifths, so plus 22 fifths. And then going the other way, it'll be m equals negative 5 over 4 root 3, not negative, sorry, positive 5, because I'm doing the opposite reciprocal. And the point doesn't change. So y minus 2 equals 5 times 4 root 3 times x minus root 3. So this will be y minus 2 equals 5 over 4 root 3x. The root 3's cancel, so this will be 5/4. And then we add 2 to both sides. So y equals 5 over 4 root 3x plus 3/8. Okay. And that was a little trickier because of the fractions and the radicals and stuff, but that's how this works with implicit differentiation. There's an example. In the next section, related rates, we're going to talk about a lot more uses of this idea of implicit differentiation. So that's it for this section. If you have any questions, as always, feel free to contact me and we can talk about them. And don't forget to do your assignments.